Hello everyone, my name is Zhang Hengchang. I am pursuing my master's degree in Tongji University. The topic of my paper is LSTM-based battlefield electromagnetic situation prediction. The outline of this speech is as follows. I will first introduce the background of the research. In the second part, I will introduce the attack-defense model. The third part covers the LSTM-based prediction method. Then I will talk about the experimental results. The last part is conclusion. The battlefield electromagnetic situation refers to the state and the development trend of the confrontation between the two sides on the battlefield. With the wide application of spectrum equipment and electromagnetic technology, the battlefield electromagnetic environment has become increasingly complex, which poses a considerable challenge to assessing and predicting the electromagnetic situation. Situation assessment process is divided into three stages: situation awareness, situation comprehension, and situation prediction. The situation prediction is the last stage of the situation assessment process. Most existing situation assessment methods focus on providing the past and current electromagnetic conditions but cannot predict future development, so it is difficult to formulate strategies based on the development trends. Therefore, accurately predicting and evaluating the battlefield electromagnetic situation has become an urgent problem in the future battlefield. In this paper, we propose an electromagnetic situation prediction method based on long short-term memory. We first build an attack-defense model based on deep reinforcement learning to simulate the electromagnetic situation. Then we use LSTM to predict the development of the situation and improve the loss function to reduce the prediction error. Furthermore, we analyze the impact of different situation features on the final win rate and use a small amount of situation information to predict the win rate with high accuracy. The experimental results show that this method can effectively predict the electromagnetic situation, providing excellent decision support for commanders. First, let me introduce the attack-defense model we used to generate data. The battlefield electromagnetic situation is obtained from the original battlefield data through data fusion methods. The deep learning method requires a large amount of data for model training. However, the battlefield data are confidential to all countries, and it is hard to get. To solve the problem of insufficient data sources, we build an attack-defense model, a type of wargaming, to generate simulated data. Wargaming has a long history. It is mainly used to simulate the battlefield environment, on which the commander can deploy their strategies and prove their ideas. The traditional wargaming model requires people to manually set the battlefield environment and manually manipulate the battlefield elements to advance the war. The cost of acquiring data in this way is unacceptable. In this paper, we build a deep reinforcement learning model to compete with each other in the simulated battlefield environment and use the data to analyze and predict the battlefield situation. The simulated battlefield consists of red side and blue side. In one game, the two sides participating in the game each has a certain number of missiles and other equipment. The game is turn-based. At each time step, we use a vector ST represent the state of two sides. The shape of ST is 3 rows and M plus W columns. The first M columns represent M types of missiles. The last W columns represent equipment other than missiles. Both sides attack alternatively. In each time step of the game, one side chooses one of its missiles to attack the other side's non-missile unit, so the decision can be denoted by a matrix. The attack decision is made based on deep reinforcement learning. We use a neural network-guided MCTS to search for the best move. The figure on the right describes the structure of the neural network. The state S is the input of the neural network. The output consists of two parts: P represents the selected strategy, V represents the prediction of the winning rate in the current state. The neural network is trained based on the data generated from games of self-play. At the initial state, the neural network's parameter is randomly initialized. Then at each iteration, multiple games are played. At each time step in one game, an MCTS search is executed under the guidance of the neural network. A game terminates when one side's total value becomes 0 or when the game exceeds a maximum length. A sample is produced at each time step. The neural network is trained from the samples to minimize the difference between the true value and the predicted value. In addition, after the attack order is issued, the attack is not necessarily successful. The success rate of the attack is related to the accuracy of the missile, the defense value of the target, and a preset parameter C. When the training of the neural network is completed, we then use the model to play more games, and use the data generated to analyze the situation. After we have the data source, this section proposes the situation prediction method based on LSTM. First, extract the situation features from the data generated from the last section. Then pre-process the data. In addition, build an LSTM model to predict the situation. The figure is the overall architecture of the proposed method, where m and n are the number of input time steps and output time steps, respectively. The data generated above represents the number and type of battlefield elements. The original data are sparse, and it is difficult to obtain the overall situation from it. We extract 15 features from the original data, including total value, number of missiles, number of non-missile units, value of ground units, etc. As a result, the situation prediction problem is transformed into a time series prediction problem, which predicts the situation of both red and blue in the future m time steps through the known situation of the red and blue sides of n time steps. The difference between the absolute values of different features is very large. For example, the number of ground units is generally dozens, but the value of total units can reach several thousand. The vast difference between different features will affect the training of the model. The feature with a larger value will occupy a larger weight in the initial stage of training, which makes it difficult for the feature with a relatively small value to play a role. Therefore, the raw data need to be normalized. We use the min-max normalization. In this question, if the 30 features are normalized separately, the contrast between the two sides will be lost. Figure 1 represents the total value of the red and blue sides of 48 time steps in one game. It can be seen that in the beginning, the total value of the red side is more than twice that of the blue side. If the two sides' features are normalized separately, after normalization, the total value is shown in figure 2. It can be seen that the total value of the two sides has both become 1 at the initial state. To avoid this problem, we normalize the same feature of both sides simultaneously. The result is shown in figure 3. This method maps the total value to the 0 to 1 interval while preserving the comparison between the two sides, and the normalized data are suitable for training in a neural network. In time series forecasting problems, RNN is a commonly used method. In recent years, RNN has achieved great success in many problems such as speech recognition, machine translation, and image description. However, RNN is hard to handle the long-term dependencies. To address this problem, LSTM introduces the cell state to maintain long-time memory and replaces the hidden layer neuron with a special LSTM structure with 3 gates, namely input gate, forget gate, and output gate. The input gate controls how much new information is added to the cell state. The forget gate decides how much cell state to forget. The output gate controls how much of the updated cell state to output. We build a neural network with 2 layers of LSTM with 128 units and 1 fully connected layer. We use ReLU as the activation function and Adam as the optimizer. Since the game is turn-based, the generated features are stepped, which makes the predicted results fluctuate. We add a penalty term to the MSE loss function to smooth the prediction results and improve the prediction accuracy. We use the data generated by self-play to train and test the LSTM model. A total of 800 games are generated. Each game contains up to 50 time steps. We randomly select 80% of the data as the training set and use 20% of the data as the test set. The batch size is set to 16. The result on the test set is shown in the first table. The input time step is 12, and the output time step is 1. After optimizing the loss function, the prediction error is reduced by about 1.3%. The figures on the right compares the result of the model with a pure MSE loss function and the model with an MSE combines penalty loss function. It can be seen that when the penalty is added, the prediction result is smoother and more close to the real situation. In the attack-defense model, a move is decided only depends on the current state of both sides and has nothing to do with the path to the current state. In the situation prediction problem, however, more input time steps can provide the neural network with more information about player preferences and equipment attributes, thereby improving prediction accuracy. We test a variety of combinations of input time steps and output time steps, and evaluate the results by RMSE. The results are listed in the second table. The results show that the larger the input time step, or the smaller the output time step, the smaller the prediction error. This shows that historical data has an impact on the forecast of the situation. Apart from the situation prediction, the evaluation of the current winning probability is also a critical subject. A proper assessment of the current situation is conducive to the formulation of the following action strategies. In the attack-defense model, the output V of the neural network gives the win rate estimation, but the input is the entire current state S. We hope to evaluate the winning probability through the situation. On the one hand, it can reduce the dimension of input data and reduce data acquisition difficulty. On the other hand, it can simplify the model and improve prediction efficiency. In the attack-defense model, the estimated win rate of the current state Vt can be obtained from the neural network. Moreover, the features can be obtained through the feature extraction process. We then take the features as input and Vt as output to train a neural network to evaluate the win rate based on the situation. We build a neural network with 7 fully connected layers with dropouts, where the activation function is ReLU, the output layer is sigmoid, the loss function is MSE, and the optimizer is Adam. We use the data of 300 games, which contains a total of 12,126 samples, to train and test the neural network. We use 9,700 samples as the training set and others as the test set. The MSE on the test set is 0.0107. We use the analysis of variance to estimate the influence of different features on win rate and denote the influence with the F value. We sort the 30 features in descending order over the F value and use the first K and last K features in as the input of the neural network to predict the win rate. The MSE on the test set are shown in the right figure. It can be seen that the MSE of prediction using features with larger F values is relatively smaller. Furthermore, as the number of input features increases, the difference of the MSE between the best and the worst tends to shrink. The MSE of the first 10 features is 0.0117, which is very close to using all the 30 features, 0.0107. In this paper, we first constructed an attack-defense model based on deep reinforcement learning and used it to generate a large amount of battle data. Next, the electromagnetic situation feature extraction method was proposed. 30 features were extracted from the original data to characterize the electromagnetic situation, and the electromagnetic situation prediction model based on LSTM was constructed. Third, we proposed a win rate evaluation model with situation features as input and win rate as output. We further used ANOVA to analyze the extracted features and showed that we could use a small number of the most relevant features to predict the win rate while maintaining high prediction accuracy. That's all. Thank you for listening.